So, good evening, everyone, and I welcome you all to today's live session of week 6 for the course Nonlinear Vibration NOC24 ME54. And this course is being taught by Professor S.K. Dwivedi of IIT Guwahati, and I'm Rashi Aditi Ranjan, a NPTEL PMRF TA and a PMRF scholar at the Department of Mechanical Engineering, IIT Patna. So, this is the sixth live session that we people are having. And these live sessions are focused on to solving questions so that it would be helpful for you to solve the assignment problems. So coming on to the overview. So talking about the overview of the things that were covered in the previous week. So the topics that were focused were the types of damping that are present in the system. Like there are various types of damping that a system can have. Like for example, the viscous damping or the Coulomb damping. Likewise, we have different kind of damping, so Rayleigh damper and like this, which we may introduce in the system in order to have a damping effect. As we know that every type of material that is being present in the environment possess some damping effect. So depending upon what kind of a behavior it is having, it may possess any kind of the damping. It may be linear, it may be non-linear, it may be discontinuous, continuous, or etc. Second that was discussed was the modal analysis. So coming on to the modal analysis, why it is required. So we know that till now the equation of motions that we have covered were actually not linked to each other, that were not coupled. By coupled, what I am trying to say is that there were two equations. One was concerned about the x1 double dot and the second one hold the x2 double dot. The equation of x1 double dot could have x1, x2 or x1 dot, x2 dot. Likewise, the equation of x2 can have x1, x2, x1 dot or x2 dot. But what if the equation of motion of x1 double dot is also having a term which is related to x2 double dot? Now, as you know, when we are solving a nonlinear equation, what we are doing we are changing the second order differential equation into two first order differential equations, and then after that we are putting it into MATLAB and then solving it by using ODE routines. But if my x1 double dot and x2 double dot, like my x1 double dot equation is also having a term of x2 double dot, which is actually a differential that I'm considering in order to integrate. So it is essential that we change this coupled equation and we decouple it in terms of x1 double dot and x2 double dot, and then we solve the equation so that it will be able to solve by the ODE function. Second, okay, second this was covered. Third was bifurcation. Bifurcation, which means that how the stability of the system was changing by change of parameter, and I'll be discussing about it further. Then it was discussed the types of fixed point, like what kind of a fixed point it is. It is a stable fixed point, unstable fixed point, saddle fixed point, it is a sink, whether it is a source, and etc. And it was covered in a very comprehensive way in the lectures. Now, last one was the basin of attraction. So in case of basin of attraction, so for example, if we have two or three fixed points, okay. So how do we know that what initial condition is going to take me to which of the stable fixed point? Actually, we cannot attain the unstable fixed point, right? Because unstable fixed point is a fixed point where the system is never going to reach. Once it diverges from that unstable fixed point, it is never going to reach that particular fixed point. But in case of stable, it can reach any of the stable equilibrium state. If there are two stable equilibrium state, depending upon the initial condition, the system may attain any of the to equilibrium state. So in that case, the basin of attraction is plotted so that we know that how the initial condition is actually varying the in order to know how the initial condition is actually varying the final equilibrium state of the system. Okay, so now I'll be taking up the questions. So coming on to the first question. So which of the following is going to affect the damping property with external stimuli? and you have four options. Okay, so there are various type of dampings as I have discussed. So first one is the viscous damping. Now by viscous damping, what I actually mean is that our damping force Fc is equals to c into x dot, where x dot is the velocity or the differential of x with respect to time, and c is my damping coefficient. So here you can see that my Fc is varying linearly with x dot. If I plot Fc versus x dot, then this is a linear graph. Okay, so this kind of damping is known as the viscous damping. So by external stimuli, what I actually mean is if I externally I apply some another kind of field or another kind of force, then what is going to happen? So it may be your electric field, it can be magnetic field, it can be visible light, it can be change in color, like that kind of things. So this viscous damping is not going to depend upon any of these kind of things. The viscous damping is only going to depend upon the damping coefficient. If the damping coefficient of a material is, for example, 10, it is always going to remain 10. No matter how much I try to provide the external stimuli, it is always going to show this kind of a linear variation. Next comes the Coulomb damping. So in case of a Coulomb damping actually comes due to the presence of frictions. For example, if there is a mass like this, and then there is this surface on which the mass is kept. Okay, so what is going to happen? If a force is applied like this on this, and for example, this mass is going to have a normal force like this, it is going to have its weight mg. So what is going to happen? If this force capital F is applied on it, a friction force is going to act on the mass like this, which is in a direction opposite to that of the applied force. Okay, so this kind of a friction force is known as the Coulomb damping, and this is a discontinuous type of damping. Why it is discontinuous? So as you know, if the velocity of this mass is in this direction, what is going to happen? If the velocity is in this direction, then the friction force is going to act in the opposite direction. Correct. Now, if after certain point of time the velocity changes its direction to this left hand side, then what is going to happen? Friction force will start acting in the right hand side. Okay, so we usually write F Coulomb damping as mu n and minus of mu n, depending upon that my velocity is in which direction. Okay, it can take these two values. It is a discontinuous function. It basically changes like this. So if this is my force and this is my velocity x dot, so it is going to be like this and then like this. Okay, no, it will be like, wait, if the velocity is positive, so if my velocity is positive, the friction force is going to act in this direction. For example, if I'm considering that the right hand side is positive, so the friction is going to act in the negative direction, this minus of mu n, and then here it is going to be mu n. So this is my Coulomb damping. Coming on to the third kind of damping, which is the Rayleigh damping, or which actually occurs in the van der Pol equation. If you people remember, as I have discussed, there was this presence of this term epsilon into mu minus mu dot cube, something like this. There was this equation which was actually changing depending upon the velocity and the conditions that the system was having. I don't exactly remember the equation here. So what was happening is it was forming the limit cycle. Okay, so there was this presence of a periodic orbit, and if my system was here, my equation of motion was forcing it to follow this. It was like this, and if my initial condition was something here, it is going to spiral out to follow this. Right. So this is how this kind of a damping is changing. So it is also not going to get affected by the external stimuli. Now coming on to the MR based damper. Now MR based damper, which is magnetorheological fluids. Okay, so what happens in the magnetorheological fluids is that if I apply magnetic field across the fluid, its properties are going to change. So it basically has a fluid, maybe some gel or something, and silicon gel or like that, and then it is going to have your iron particles in it. So what is going to happen? Particle is going to get attracted with the magnetic field, right? So if I apply magnetic field across that material, the iron particles are going to align itself in some particular pattern and everything. So what is going to happen? The property of fluid is going to change. Whatever shear modulus it is possessing, it is going to change, isn't it? So because of that change of the property of the system, its damping effect is going to change, isn't it? So what happens in the MR-based damper is that with the change of magnetic field, its damping effect is going to change. Okay, so it is also known as an active damper, and the magnetic field is going to act as an external stimuli. Your magnetic field is your external stimuli, isn't it? And your iron particles will be affected by the field. Okay, so if I talk about just its application, so I'll just write it here. It's an active damper. Many car manufacturers, like for example, if I take very big car companies like I'm not able to recall the name. Okay, if I'll remember, I'll tell you. So those cars, they basically use these kind of active dampers. Okay, why? Because then it would be helpful for to reduce the jerk and the vibration that are being encountered by the cars, and it has a very wide range of application apart from being used as a damper in the cars. It can also be used as a damper in case of the machines basically they have some kind of a vibration induced in it, okay, because of its operating condition, because it has some motors in it. It is going to produce some oscillation because of motors that are having gears and everything. It is not possible that we make a very ideal axle or very ideal gear, okay. There is some eccentricity due to the mass, which is going to create some kind of a vibration, and that vibration will get transmitted through the floor. Okay, so in order to reduce the transmission of the vibration, these MR-based dampers can be used, so that depending upon the vibration amplitude and frequency, we can actually tune the damping effect of the MR-based damper, okay, in order to achieve efficient damping property. Okay. Now I'll have a brief discussion about bifurcation, since if you would have seen your assignment also, that your most questions of the assignment are actually based on the concept of bifurcation. Okay, so I'll briefly explain about 2 to 3 types of bifurcations, and how do we know that whether the bifurcation which is giving which kind of a fixed point, and that particular type of fixed point is a stable fixed point, it's an unstable fixed point, and everything. Okay. So coming on to what is bifurcation. So if you people remember, as I've discussed in my, I guess, week 2 live session, that the best example in to understand that what is bifurcation is the buckling of a beam. So if I have a mass over here and then I have a beam like this, okay, it is like this. The mass is being balanced by the beam. Okay, but if this mass is increased to, let us say, capital M, what is going to happen? This beam, which was first like this, straight, it is going to buckle. Okay, but it would depend that in which direction it could buckle. It may buckle like this, bend like this and it may bend like this. It would depend. Okay. So, and your capital M is greater than small m. It would depend on many factors. So you can see that as your mass is increased, the stable state of the system or the equilibrium state of the system actually changes. Initially, the beam was straight and now it has buckled. But when it has buckled, it is going to have two kind of bending. Either it can be bent in the right direction or it can be bent in the left direction. Okay, so what has happened? Initially, there was one stable equilibrium point, and after the increase of mass, it led to two stable equilibrium point. So what actually happened? If you can see what actually happened. So what actually happened is that with the increase of mass, the equilibrium property of the system has changed. Correct? So it is essential that we study that how this is actually happening. Okay, because if the equilibrium state is actually changing like this, it may happen that we can experience any catastrophic failure, isn't it? And it is important that we avoid that kind of a failure. Okay, so that is why it is important to study bifurcation. So, considering the first kind of a bifurcation, which is the saddle node bifurcation. Okay, so I'll just discuss briefly. First one is your saddle node. Okay, so what happens in this kind of a bifurcation is that if I write the normal form, it is written like x dot is equals to r plus x square. See, what I'm talking about, the bifurcation is all are one dimensional. Okay, one dimensional because I have only the velocity which is written in terms of the position. Okay, so first I'll describe this, and then with the help of the question, I'll tell you that how you are going to deal with the second order systems. Okay, so x dot is equal to r plus x square. So first thing is that you find the equilibrium states. Okay. So in order to find the equilibrium state, what I'm going to do, I'm going to let x dot is equals to 0, which implies r plus x square is equals to 0, which gives my equilibrium state as plus minus under root of minus r. Now my r can be positive, it can be negative, and it could be 0. Okay. So what is going to happen? So if you'll see that we have a under root over here. Okay. So this is a equilibrium state or a fixed point or a place where the force balances itself. Okay. So if I'm having under root of minus r, can I have an imaginary fixed point? That is not possible. Physically also it is not possible. Can you have an imaginary fixed point? Can you have an imaginary position? That is not possible. Okay. It should always be real. So you'll see that I'll have my like the fixed points exist only if r is less than 0, isn't it? If my r is less than 0, then it is some negative value, then some negative value multiplied by minus would be some positive value, and then I'm going to have some positive value inside the under root. So then only I'm going to have a fixed point. Okay, so one thing is clear that my fixed points are going to occur only if r is less than 0. Now coming on to finding that how the stability is changing. Okay, I know that I'm going to have no fixed point for r greater than 0, and I'm going to have two fixed point for r less than 0. But what happens to the stability of those fixed points? Whether it is stable, unstable, saddle, or whatever. So let us find out. So first is that I find the Jacobian. So how am I going to find the Jacobian? So if my this x dot I assume is equals to f of x, then in that case my Jacobian is this, which will be equal to 2x. Okay. So if my this term is positive, so I'm going to have two roots, one positive and one negative. So you'll see that if this x is positive, my Jacobian is positive, my Jacobian is positive, which means that that is a unstable case. And while if my x is negative, it's a stable case. If you remember that I discussed it in the previous live session, that how with the help of Jacobian we can find whether the system is stable or unstable for a corresponding fixed point. Okay, we were actually linearizing the system with the help of the Jacobian, and then we were finding the how the Jacobian was actually changing. Okay, so you can also consider it like eigenvalue also, because in the previous case, in the previous session we had a 2 cross 2 matrix where we were finding the eigenvalues. Here also you can consider the eigenvalue. I didn't introduce it because see, when I was introducing the eigenvalue for a matrix, it was j minus lambda I determinant is equal to 0. In this case, my j is a 1 cross 1 matrix. You can say it's a 1 cross 1 matrix. So what is going to happen? I have to write j minus lambda is equals to 0. So my lambda is going to be what? It is going to be the Jacobian itself. So that is why I'm considering this. Okay. So if it is positive, then that particular branch is unstable, and if it is negative, then that particular branch is stable. You'll see that in case of a linear system, when we are having a linear system, what was happening? My fixed point was actually not changing, isn't it? If my, in this case also, if I had x dot is equals to r plus x, was my fixed point changing? No, my fixed point would be same. Okay, no, it would be like if r is considered as a constant value, I'll consider r as 1. So then 1 plus x is going to be 0. My fixed point was not changing, but since I have now introduced r, it is going to change my fixed point as r is changing. Okay, and my when my r is changing and my fixed point is also changing, what is actually happening? A certain parameter is actually changing the stability of the system, and this phenomena is known as bifurcation. Okay, that the change of a certain parameter in the system is actually going to change the equilibrium characteristic of the system. Okay, so now there is a positive. When it is positive, it's an unstable branch, and when it is negative, it's a stable branch. Okay, you can also consider this by plotting. So for example, I'll consider three cases. First one is when r is less than 0, what is going to happen? How is the plot going to be? R is less than 0, I'm going to have two equilibrium points, correct? One positive, one negative. Okay, and apart from that, how is it going to vary? So it is going to be like this. This is my x, this is my x dot. I'm going to have these two equilibrium points. So if you remember, as I discussed, if my velocity is positive, then it is going to be like this, the arrow. Talking about if velocity is positive or negative, I'll just recall you that if the velocity is positive, my system is going to move farther away from that particular fixed point. If my velocity is negative, my system is going to take itself to the fixed point. Okay, so this is what the case is. And then here it is negative, so it is going to be in the left side, and then here it is positive, it's going to be in the right side. So you'll see that this is a stable fixed point and this is an unstable fixed point. So this is when r is less than 0. Now when r is equal to 0, what is going to happen? I'm going to have only one fixed point, whether it is stable or unstable. So if you will plot, you can get to know from. Okay, so here you can see, as you can relate it to the Jacobian thing, that this is the case when my Jacobian is negative, right? And from the graph also you can see that the negative fixed point is actually stable. And here you can see that my Jacobian is positive and this is a positive fixed point. And from the graph also you can see that it's a unstable fixed point. Okay, so you can choose any of the two analogy. Usually if your equation is simple and you can go through the plot, it is better that you use the plot. But if your equation is very complex, it is having so many terms, and apart from that, if it is having some transcendental terms also like sine, cos, tan inverse or something like that, then in that case it is preferable that you use the approach of Jacobian. And also if you have these kind of transcendental terms, then it is preferable that you go with the numerical technique. Okay, that also I'll discuss for the last questions that I have choose to discuss. Okay, so now what is this fixed point, whether it is stable or unstable? So if you will see that the velocity here is positive, so the direction is going to be like this, and here the velocity is, okay, sorry, velocity again here is negative, sorry, positive. It is again going to be like this. So this is your half stable fixed point, and we usually plotted like this, the half stable fixed point. Okay, it is stable for r less than 0, but it becomes unstable as soon as r increases, even for a very small amount greater than 0. And the third case is when r is greater than 0, you know that there is going to be no fixed point, because this equation is giving some imaginary value. Okay, so this is how the plot is going to be. And if you are if you can, if you want, you can also plot the variation of x with r. So how is it going to be? It is going to be like this. This is going to be your r, this is going to be your x, and you can see that your negative one is a stable and the positive one is an unstable fixed point. This is your unstable, this is your stable. And this kind of a bifurcation is known as your saddle node bifurcation. So in case of a saddle node bifurcation, there is one stable and a one unstable fixed point, and then what do? They come together and then they result in the vanishing of the fixed points. After that, there is no fixed point. Okay, so coming on to other kind of bifurcation. So this was the saddle node bifurcation. I hope it is clear. I've already discussed this earlier also. Okay, so coming on to the transcritical bifurcation. So in case of transcritical bifurcation, I can write the normal form as Rx minus x square. Now you people must have understood that your R is the parameter. Okay, so these normal form are essentially given in order for you to understand that how the bifurcation is actually happening in simple form. And then if you have an understanding that of how the bifurcation is actually occurring in the system, then you can also solve it for the complex equations. Okay, so for the transcritical bifurcation, if you find the fixed point, it will be r x minus x square is equals to 0, which implies x into r minus x is equals to 0. So x is equals to 0 and x is equals to r. These are your fixed point. Now talking about its stability, I'll find the Jacobian, which will be again del f by del x, and it will be r minus 2x. Okay, so you'll see that we have two fixed points. One is 0 and the other one is r, which would change with the parameter r. Okay. So coming on to the stability of the first fixed point, which is x is equals to 0. So for x is equal to 0, your Jacobian will be equal to r. Okay. So depending upon the value of r, my first fixed point, which is 0, will be stable or unstable. So if my r is less than 0, is a stable fixed point. And if r is greater than 0, then x is equals to 0 is an unstable fixed point. Okay, I hope that it is clear. So this is the thing. And then now if I talk about my second fixed point, which is for x is equals to r, my Jacobian will be equal to r minus 2r, which will be equal to minus of r, isn't it? So in this case, if my x is less than, oh sorry, if my r is less than 0, what is going to happen? My Jacobian will be a positive value, and so this x is equals to r will be an unstable branch. Okay, so in this case, if r is less than 0, then x is equals to r is an unstable branch. And if r is greater than 0, then x is equals to r is a stable branch. I hope that this thing is clear, that how we are actually relating it with the Jacobian. Now, you can again use the concept of graph for finding out that how it is actually changing. So I have x dot. The first case is when r is less than 0. Okay, so I'll have two fixed points. One will be minus r and the other will be 0. So if you remember how the variation is going to be, the arrow is going to be here. So you will see that for x is equals to r, the system is actually diverging, and for x is equals to 0, the system is converging. So this is your unstable fixed point and this is your stable fixed point, 0 and r, which we also obtained from the Jacobian. Okay, concept of Jacobian. And then your case when r is equal to 0. So when r is equal to 0, you are going to have only one fixed point like this. Okay, and whether it will be stable or unstable. So it is again a half stable fixed point. And then coming on to the case when r is greater than 0, I am again going to have two fixed points, something like this. This is going to be your r. This becomes stable now, and this becomes your unstable fixed point. You can also see it from the arrow sign. Okay, and if you want to plot x with r, how is it going to be? This is your r, this is your x. So you have two fixed points. One is x is equals to 0 and the other one is your r. Correct. So what is actually happening? First, you'll see that for r less than 0, my x is equals to 0 is the stable fixed point. Correct. Isn't it? And then for my r greater than 0, my 0 becomes unstable and my r becomes stable. Isn't it? So how is the plot going to be? So I have x is equals to r, which is this. Okay. And then I have stable one. So when this branch becomes stable for x greater than 0, and when this branch is stable for mm, this branch becomes stable for r less than 0. Okay, so this is what it's the transcritical bifurcation. Now coming on to the pitchfork bifurcation, as you remember, pitchfork bifurcation are divided into two categories, the supercritical and the subcritical, depending upon the characteristics. So first I'll talk about the supercritical. So the normal form for the supercritical pitchfork bifurcation is essentially given as x dot is equals to rx minus x cube. So in this case, if I want to find my fixed point, it will be x dot is equals to 0, which implies r minus x square into x is equals to 0. So from here, I'll have my fixed point as 0 and x is equals to plus minus of under root of r, isn't it? So I have three fixed points. So from here also, you know that three fixed points will be there if r is greater than 0. If r is less than 0, this becomes imaginary and I'm going to have only one fixed point. Now coming on to the stability. Now if I find Jacobian, which will be equal to r minus x square. So coming on to for x is equals to 0, what am I going to have? My Jacobian is equals to r. So if my r is less than 0, I'm going to have 0 as a stable fixed point, and if my r is greater than 0, then my x is equals to 0 is an unstable fixed point. So r is positive, x is equals to 0 is unstable, and r is negative, then x is equals to 0 is stable. Okay, and similarly for x is equals to, let us say, you can consider for both plus minus r together, because your Jacobian is r minus x square. So whether you consider plus under root r or whether you consider minus under root r, the Jacobian is going to be the same. Okay, so I'll have for x is equals to plus minus under root of r. My Jacobian is given as r minus, okay, I missed a 3 over here, right? 3r, which will give me minus 2 times of r. So you'll see that if my r is less than 0, my both these actually, that is not even the case, because if my r is less than 0, these equilibrium points are not going to even exist. So stable or unstable, that is not even a question. But now considering that if my r is greater than 0, you'll see that your Jacobian will be negative for both these cases, and hence for r greater than 0, both plus minus under root of r will be stable fixed points. Clear? Okay. So you can see this by the graphical method also. So basically here I'm trying to relate that how we are actually using the Jacobian concept in order to predict whether a particular fixed point is going to be stable or unstable. So for r less than 0, I'm going to have only one fixed point, okay, which is x is equals to 0. So the plot would be something like this. You can actually use MATLAB and see that how this variation is actually happening, how the plot is going to look. Okay, it will give you a proper precise graph, isn't it? It will be something like this, and here you can see that your variation will be like this, and here. So this will be my stable fixed point, which I have also seen through the concept of Jacobian also. For r greater than 0, or let us first take for r is equal to 0, the plot is going to be almost the same, only this is going to be much more steep, like this. Again, it is going to have this as a stable fixed point. Now coming on to for r greater than 0. Okay, I'll just make it here. For r greater than 0, the variation of x dot and x is going to change. Okay, it is going to be something like this. Now if you'll see that the stability of the fixed point, which is 0, it is going to change. You'll see that both the arrows are actually diverging from 0. So this becomes a unstable equilibrium state, and this, your plus under root r and minus of under root r, are going to be your stable fixed points now. Okay, and you have also seen this through the use of Jacobian. Okay, and if I want to plot the variation with respect to r, so you can see that till r is negative, I have this as a fixed point. After this, my this becomes unstable, and I'm going to have two branches of stable fixed points, and that is why we call it as a pitchfork bifurcation, because you can see it looks something like a fork. Okay, so your subcritical pitchfork bifurcation is somewhat similar to that of a supercritical. The only variation is that in the plus and minus. So in supercritical, you were having a minus sign. Now in case of a subcritical, you are going to have a plus sign. Your x dot will be equal to rx plus x cube. So from this, you can intuitively see that now what is going to happen. Now you're going to have three fixed points for r less than 0. Initially, there were three fixed points when r was greater than 0. Now you are going to have for r less than 0. But coming on to the stability, that what is going to be the stability? So we'll just check. Okay. So this implies r plus x square into x is equals to 0. So you are going to have x is equals to 0. And then you are going to have x is equals to plus minus of under root minus r. So there will be three fixed points for r less than 0. Okay. And for r greater than 0, there will be only one fixed point, and which is 0. Okay. Now checking about the stability. So Jacobian will be equal to r plus x square. So for x is equals to 0, again I have missed a 3. For x is equals to 0, I'm going to have j is equals to r. So for r greater than 0, x is equals to 0 is unstable, and for r less than 0, it is stable, isn't it? So I'll just write if r less than 0, x is equals to 0 is stable, and if your r is greater than 0, x is equals to 0 is unstable. Okay, now coming on to for my Jacobian is going to be, you have r, then plus minus this, and plus 3 times of you have r, which is going to be your 4. No, you're going to have a minus over here, correct? Minus 2 times of r. So firstly, you are going to have the fixed point plus minus under root of minus r only if r is negative. And you can see from here, if r is negative, the Jacobian comes out to be positive, which means that both these plus minus under root of minus r are unstable fixed points. For r less than 0, Jacobian is greater than 0. So plus minus unstable. Okay. And if you want to see, you can see its plot. It is going to be like somewhat like this. And if you'll see that how the variation is going to be, it is going to be like this. So this becomes your stable, this becomes unstable, this becomes unstable. This is x dot. Okay, and then similarly, you can see that as this is for r less than 0, if r is equal to 0, the variation will go like this. And then similar behavior is going to exist for this becomes your unstable. Similar behavior is going to occur for the other fixed points, other cases of r. So this is your subcritical bifurcation, and you can see that in case of a subcritical bifurcation, the variation is like for value of r less than 0, there is stable fixed point, but as soon as the value increases, it leads to what? It leads to instability, isn't it? The system becomes unstable, which is what we don't want. Okay, I don't want the system to go to instability, and this kind of bifurcation is also going to cause your kind of a bifurcation is also going to cause catastrophic failure of the system. Okay, now I'll start taking up the questions. I hope that it is clear. If these things are clear, then we'll be able to solve the questions very easily. Okay, so for the equation of motion, x dot is equals to r minus x squared, which of the following is correct? So if you remember, this is the case of here. There is a bit difference. Here it is a minus. Okay. So, but this is a case of a saddle node bifurcation. How? We'll just see. So you have x dot is equals to r minus x square. Okay. So my fixed points are going to be what? Okay. So for r greater than 0 only, I'm going to have the fixed points. For r less than 0, I'm not going to have any fixed points. So coming on to the option, I have system has two stable fixed point for r. Okay, we'll just check the stability also. Okay, so the Jacobian will be equal to minus of 2x. Okay, so I'm going to have this plus minus under root of r. So from here you can see that if my x is negative, okay, it will be unstable. Why? Because my Jacobian is positive. And if my x is positive, it will be stable. And if I go into plotting it, if I want to plot it, this is r and this is x. Okay, so for till r is equals to 0, I'm going to have no fixed point. And after r increases from 0, I'm going to have two fixed point. Now among them, which one is stable and which one is unstable? So you can see here, if my x is negative, that is the negative part is what? Negative part is unstable. It becomes unstable while my positive one is stable. So I'll make it as a continuous line. So this is my stable and this is my unstable. And this is also a case of saddle node bifurcation. See, both when two fixed points, one stable and one unstable, it comes together and leads to vanishing of the fixed point, or with the increase of parameter, there is no fixed point initially, and then there is the birth of two fixed point where one is stable and the other one is unstable. Both are the cases of saddle node bifurcation. Okay, both can occur anyway. Okay, either there is no fixed point and then there is two fixed points, one stable and unstable, or either when there is two fixed points, one stable and unstable, and then they come together and lead to no fixed point. Okay, so coming on to the option, system has two stable fixed point for r greater than 0. No. System has no stable fixed point for r greater than 0. No. System has one stable and one unstable equilibrium point for r greater than 0. This is your correct option. Okay. And saddle node bifurcation occur here. Yes, this is a case of a saddle node bifurcation. Okay. Coming on to the third question. Okay. This is the direct case of a saddle node bifurcation. Okay. So I'll not discuss much about it. I'll just make a graph and then you people will be able to understand that what is actually happening. So if you remember, the fixed point would exist only if my r was less than 0 and my lower branch was stable and the upper branch was unstable. Okay, so coming on to the options, system has two stable fixed point for r greater than 0. This is incorrect. System has no stable fixed point for r greater than 0. This is the correct option. Then system has one stable and one unstable fixed point for r less than 0. Yes. And saddle node bifurcation does not occur here. So this is the wrong option because this is also a case of a saddle node bifurcation. Both ways, it is going to be the saddle node bifurcation. Okay, so if this kind of a behavior is seen in any kind of a nonlinear system, then we can say that there is the occurrence of a saddle node bifurcation. Coming on to the fourth question. Okay, so the parameter mu of the system is varied, then it would result in the Hopf bifurcation for which of the following? So first of all, what is a Hopf bifurcation? So Hopf bifurcation is actually a dynamic bifurcation. Okay, the bifurcations that we have studied over here, they were divided into two cases, static and dynamic. By static, we actually mean is that the system is attaining a fixed point exponentially. Okay, but in case of a Hopf bifurcation, there is existence of orbit, periodic orbit. Okay, so if I say that bifurcation can be of two types, static and dynamic. Okay, so static case is going to have all the things that I discussed, your saddle node, transcritical, pitchfork, while your dynamic is going to have the Hopf bifurcation. Okay, so from here it is clear that okay, in the dynamic case, I'm going to have a existence of a periodic orbit. Okay, so from these options I can try. Okay, so and secondly, the eigenvalues are changing. You'll see that there are two eigenvalues, which means this is a 2 degree of freedom system. Okay, two-dimensional system. So that is why there are two eigenvalues. Okay. Secondly, if I want to find that if it is a Hopf bifurcation or not, I'm actually trying to see that whether there is occurrence of some periodic orbits. And if you remember that in the lecture it was discussed that the periodic there is some occurrence of a periodic orbit in case of a Hopf bifurcation, isn't it? That the system was actually having a unstable state, unstable kind of a spiral, and then it resulted into a stable fixed point, or it was having a stable fixed point and then it went into an unstable spiral, or these kind of a things. So we'll just try to see that how by watching the eigenvalues I can actually predict. So coming on to the first option. So eigenvalue varies from 0.1, 0.1 to 0.5 and 0.3. So from here you can see that initially the eigenvalue was 0.1 and 0.1, which means that the eigenvalues were both real and positive, which means that both this my fixed point is unstable, or it was unstable, isn't it? Because both the eigenvalues are positive, which means that my response is something going to be like a summation of two positive exponential functions. Okay, which is as time is going to infinity, it is going to go to infinity, so my system is going to diverge. And now it has come to minus 0.5 and minus 0.3. So it has actually come to a stable state because now my eigenvalues has become negative. So now whatever the perturbation I'm going to give to the system, it is going to take the system from that particular initial state to the fixed point. Okay. So this is not the case of a Hopf bifurcation. Right. Coming on to the second option, so eigenvalue value varies from 1 on minus 1 to 2 comma 2. Here what is happening? The system was initially a saddle point, like the fixed point was initially a saddle point. How saddle? As I discussed in the previous week's live session, that if one eigenvalue is positive and the other eigenvalue is negative, then it means that the fixed point is a saddle fixed point, which means that the system is never going to attain it. In one direction of the eigenvector, it is going to try to reach to that point, but after some time, the dominance of the positive eigenvalue is going to increase, and that is why it is going to take the system to infinity again. That is, it is never going to achieve the fixed point. So it is changing from saddle to unstable fixed point, isn't it? Both my eigenvalues are becoming positive. It is going to take the system to infinity. Coming on to the third option, which is the eigenvalue varies from minus 1 plus 2i and minus 1 minus 2i to minus 0.5, minus 0.01. What is happening here? The system was initially oscillating and then it went to a this stable fixed point. Okay. Now coming on to the fourth case, eigenvalue varies from 1 minus I and 1 plus I to minus 1 minus I, minus 1 plus I. So what is going to happen in this case? If you see that initially the real part of the imaginary eigenvalue was positive, so it was making a unstable spiral. It was making a unstable spiral, something like this. Okay, and now the eigenvalue has changed to a stable spiral because both my fixed point, sorry, both the real part of my eigenvalues has become negative. So this is a case of a Hopf bifurcation. It is changing the system dynamics. It is a dynamic kind of a vibration. So this is my case of a Hopf bifurcation. Coming on to question number 5. So which of the following option gives the equilibrium point of the set of the equation given us? Okay, so if you have a nonlinear system, it is essential that to a set of equation you need to find the equilibrium points. Okay, if you're not going to find the equilibrium points, how you are going to analyze it? Right. So this is a very easy question, but still we'll just discuss it. I'm going to have two nonlinear algebraic equation. However, it's an easy equation, although you can have a much complex equation that would be nonlinear. It can be have transcendental terms as well, but this is a very easy case. So in the first equation, what can I do? I can take x as common. In the second equation, I can take y as a common, so it can become 4 minus 6y plus 3x is equal to 0. And here I'll take y common. Okay, so you'll see that for the first equation, we can have two options. Either my this thing is 0 or my this thing is 0. So first I'll consider that my x is equal to 0. So if my x is equal to 0, then I would like to find what is y. So if for that I'll consider that my y is not equal to 0. So what is going to happen? This is going to go to 0. My y minus 2 plus 2, yes, 2x is going to go to 0. And then I have x is equal to 0. So I'll have y minus 2 is equal to 0. Y is equals to 2. So my first fixed point is 0, comma 2. This one is correct. So I have my first fixed point as 0, comma 2. Second is the case when I can consider that my y is equal to 0, isn't it? I can consider that my y is equal to 0. And there is also a case when x is equal to 0 and y is equal to 0, but it's a trivial solution. Okay, so I don't have to discuss that. It's a trivial solution. Okay, okay. So your x will be equal to 0, y is equal to 0, and this both the algebraic equations are going to satisfy it, and that is why it is also known as a trivial solution. So 0, comma 0 is a correct answer already. Okay, now if I consider that my y is equal to 0 and my x is not equal to 0, so then what is going to happen? I'll try to solve it. So I'll have y 4 minus 6y plus 3x is going to be equal to 0. So in this case, what is going to happen? My y is 0, so I'll have 4 plus 3x is equal to 0. So x will be equal to minus 4 by 3. So my second fixed point would be minus 4 by 3 comma 0, which is option C. Done. Now coming on to the case when I consider that both my x is not equal to 0 and both the y is also not equal to 0. So in that case, I'll have to solve this equation like this. Since x is not equal to 0, y is not equal to 0, so these two are going to go to 0. 0 and y minus 2 plus 2x is equal to 0. So what can I do if I want to solve it? I'll do one thing, I'll just multiply that with 6. So this is going to give me 6y minus 12 plus 12x 4 minus 6y plus 3x is equal to 0. So I'll just add this. What is it going to give me? 15x minus 8 is equal to 0. So I'll have my x is equal to 8 by 15. I'll put the x, any of the equation you can put it in. Let us put it in this equation. So I'll have y minus 2 plus 16 by 15. So I'll have y is equals to, so this is going to be 15 into 2, which will be 30 minus 30 plus 16, 14. So y is going to be 14 by 15. Okay, so one of your fixed point will be 8 by 15 and 14 by 15. This is your D option. Okay, so this is how you need to find out that what are the equilibrium points, because in case of a nonlinear system, it is very important that we know that what are the fixed point, and then only we can take out that how the stability of the system is going to be. Because if we miss any of the fixed point, it may happen that we can do the wrong analysis. So it is essential that we consider all the cases, whether it is trivial or non-trivial case, for the fixed point that we get, and then after that we can analyze that what is the stability. For example, if I want to know that what is the stability of these four fixed point, what would I do? I'll first find the Jacobian. Now in this case, it is, since it's a two-dimensional case, my Jacobian is going to be a 2 cross 2 matrix. Okay, Jacobian is going to be a 2 cross 2 matrix. Okay, because I'll define Jacobian as del f by del x, del f1 by del y, and then I'll have del f2 by and del f2 by del y. This is going to be my Jacobian, and then after finding the Jacobian, my Jacobian will be in the form of x and y. So in order to analyze the stability of a particular fixed point, I'll put the value of x and y. For example, I want to see for 0, 2. I'll put x as 0, I'll put y as 0, then I'll find the eigenvalue, and from that I'll be able to know that for this particular given equation and the particular fixed point, whether the system is going to be stable, unstable, or whether the fixed point is saddle, etc. Okay. Also, if the equation is complex and it has transcendental terms, so you can use MATLAB in order to find the solution. Okay, so you have many numerical techniques like the Newton-Raphson technique, etc., which you can use to find the fixed point in that kind of a equation. Okay, so coming on to question number 6, which of the following bifurcation may be observed for x dot is equals to this? Or let us do one thing. I'll just discuss one with you. It will be easy for you, isn't it? So you have your f1 as 4x minus 6xy plus 3x square. And then you have your f2 as y square minus 2y plus 2xy. So if you want to find the Jacobian, what is it going to be? So first one is the differentiation of f1 with respect to x. We'll have 4 minus 6y plus 6x. Then you'll have the differentiation with respect to y, which will give you minus 6x. Then here you're going to differentiate with respect to x, 2y, and then differentiation with respect to y, 2y minus 2 plus 2x. Okay. So if I want to know about the stability of, for example, let us say the trivial solution 0, 0. So my Jacobian would become 4, 0, 0 minus 2. Now I can find my eigenvalue. I'll just find the determinant of j minus lambda I, which would give me 4 minus lambda into minus 2 minus lambda is equal to 0, from which I'll get lambda is equals to 4 and lambda is equals to minus 2. So you'll see that one of the eigenvalue is positive and the other eigenvalue is negative, which means that my fixed point 0, comma 0 is a saddle, isn't it? Likewise, you can also find for, let us say, 0, comma 2. So my x is 0 and my y is 2. So in that case, my Jacobian will be what? My x is 0 and y is 2. It will be 4 minus 12, which would give me minus 8. Then x is 0, y is 2. This will be 4, 0. And then I have here 2 into 2, which will be 4. Okay, so this would give me, if I apply again determinant of this would give me what? This would give me minus 8 minus lambda into 4 minus lambda, which will result in lambda is equals to 4 comma minus 8. Again, the 0 comma 2 is again a saddle. So likewise, you can see that about the stability. Okay, coming on to question number 6. Okay, so you have to find that which kind of bifurcation this is going to have. Okay, so see, it is very essential that for finding out this which kind of bifurcation is actually occurring in the system, you also need to know that what is the critical value of the parameter. Now, by critical value of the parameter, I mean that what is the value of the parameter after which or at which the there is change in the number of the fixed points, isn't it? Till now, the examples that I have taken, okay, so till now, the examples that I have taken, the critical parameter value was 0, isn't it? The critical value was 0. At r is equal to 0, there was, you can see here, let us come here, see, the change in the system's equilibrium state was happening at r is equals to 0. Here also at r is equal to 0, at r is equal to 0, at r is equal to 0. Okay, so my r is equal to 0 was my critical value of the parameter. But that is not the case every time. So here we'll first have to find out that what is the critical value. Okay, so if my x dot is this, I'll try to find out the equilibrium points. What is it going to be? Okay, so one fixed point is going to be minus 1. The other one would come from here, which will be equal to x plus 1 square is equal to mu. So my x plus 1 will be equal to plus minus of under root mu, and my x is going to be 1 plus minus under root of mu. So what is the critical point over here? If you'll see that the critical point over here is going to be again mu is equal to 0, isn't it? Because your this x is equals to minus 1 is going to be always there, irrespective of the value of mu. But these 2 points, these 2 fixed points are going to depend upon mu. And again, if my mu is less than, okay, thank you. Okay, so it would depend upon mu. So if my mu is less than 0, what is going to happen? If a mu is less than 0, these fixed point are not going to exist because it would give me an imaginary value and imaginary fixed point does not exist. So mu should be greater than 0 in order to in order for these fixed point to exist. So again, my critical value of the parameter is going to be 0. In this case, it is equal to 0. Okay, so it is essential that you identify that what are the critical point. So it is 0. So now I have to find out that which kind of bifurcation is actually occurring over here. Okay, so what would I do? Definitely I'll find the Jacobian, I'll put into this and then I'll see. So my Jacobian will be equal to, however, if you'll see the equation, you can actually predict that which kind of a bifurcation it is, because it is a very simple equation. However, I'll just take this. So I'll have the Jacobian as minus 3 x plus 1 square, and then I'll have plus mu. So this is my Jacobian. Right. So coming on to first, x is equals to minus 1. So for x is equals to minus 1, my Jacobian will be equal to mu. So if my mu is positive, my x is equals to minus 1 is unstable. If my mu is negative, my x is equals to minus 1 is stable. So x is equals to minus 1 is stable for mu less than 0, and it will be unstable for mu greater than 0. Okay, now coming on to for x is equals to minus 1 plus minus under root of mu. Okay, if you'll see for this, the Jacobian will be equal to what? Again, in this case also, the Jacobian is going to be same for both plus 1 minus 1 plus minus under root of mu, because if you see that if you put x in the Jacobian equation, this is going to cancel out and you'll have plus minus under root of mu here, and it is going to get squared up, so it is going to give you minus 3 mu plus mu, which will be minus 2 mu. Right. So here also you can see that for mu less than 0 is not even a case for us to discuss. We'll have only mu greater than 0, because only after that the system is going to have the fixed point. And if my mu is positive, both the roots minus 1 plus minus under root of mu is going to have a mu greater than 0, both going to be stable. So what do you think? What kind of a bifurcation it is? If you see for mu less than 0, we are having only one fixed point, and that is also stable. While if mu actually increases from 0, that x is equals to minus 1, which was initially stable, becomes unstable, and then there is introduction of two new fixed points which are now stable. So this is a supercritical pitchfork bifurcation. Okay, if initial my this x is equals to minus 1 would have been unstable for mu less than 0, let us suppose, and then after the introduction of two new equilibrium states, and this my x is equals to minus 1 then becomes stable, and my these two new fixed points are still are unstable, then that would be a case of subcritical pitchfork bifurcation. However, for this equation, it is a supercritical pitchfork bifurcation. Okay. Also, you can see this by use of MATLAB. I'll just take up MATLAB for that. Okay. First, I'll discuss the other two questions, and then I'll use MATLAB in order to tell you that how you can actually use MATLAB in order to predict the stability of the system. Okay. So now I have this equation. Okay. First, I have to find the critical value of R and what bifurcation occurs in the system with the change of parameter. Okay. Now this is a different system from whatever we have discussed up till now. It is a different case. Okay. So now we'll try to find that how we are going to deal with this system. So I have x dot is equals to 0. It is going to give me my fixed point. So I have x plus rx by 1 plus x square is equals to 0. What would I do? I'll multiply it. I'll write it like 1 plus x square into x plus Rx is equals to 0. I'll take x as common, so I'll have 1 plus x square plus R is equal to 0. Okay, so I'll have three fixed points. One is going to be 0 and the other one is going to be, from here I'll get isn't it? These are going to be my fixed points. Now, critical value. Critical value is what? When this fixed point exists. Okay, so this fixed point is going to exist when my 1 plus r is negative. Only then the negative multiplied with some negative value is going to give me a positive value. So my minus of 1 plus r should be greater than 0, or my 1 plus r should be less than 0, or my r should be less than minus 1. So this gives me the critical value, which I can say RC, critical value of, no, self should be, this is the case, and my critical value RC is equals to minus 1. Okay, now coming on to how the system is going to behave. So for that I'll find the Jacobian. So the Jacobian would be 1 plus differentiation of first function, which would give me r into 1 plus x square, and then I'll have a minus, then I'll have rx into 2x whole divided by 1 plus x square whole square. Correct? This is going to give me 1 plus, this is going to be r plus rx square minus of this. So it is going to be r into 1 minus minus x square divided by 1 plus x square whole square. Okay, now I'll try to find that how my system is actually behaving with the change of parameter. Okay, so I'll write the Jacobian equation here once again, which is my j is equal to 1 plus r into 1 minus x square divided by 1 plus x square whole square. Now I have for x is equals to 0. My Jacobian is going to be what? If I have x is equals to 0, you'll see that this x is going to be 0, this x is going to be 0, so I'm just going to have 1 plus r. Okay, and you know that my limiting case is r is equals to minus 1. Okay, so depending upon the value of r, I'll have that whether my this x is equals to 0 is stable or unstable. So you'll see that when r is less than minus 1, x is equals to 0 is stable because my Jacobian is going to be negative. And if r is greater than 1, my x is equals to 0 becomes unstable, right? So this was for x is equals to 0. Now coming on to the other two cases when my x was what? When my x was this, plus minus under root of, okay. So in this case, if I want to find the Jacobian, okay. So I'll just do the one thing, I'll just consider a value of r, okay. Well, I should say I'll consider a, fine. So firstly, r should be less than minus 1. That is a very logical condition. R should be less than minus 1, whatever the case is. If r is greater than minus 1, then simply our system is not going to have these two equilibriums. So r should be less than minus 1. So let us consider r is equal to minus 3. Okay, and let us see what is actually happening. So if my r is equal to minus 3, what is going to be my fixed point? It is going to be x is equals to plus minus of, isn't it? So if now I'll put it in the Jacobian, what am I going to get? I'll have 1 plus my r, which is minus 3, and then I'll have 1, and then I have minus of x square, which is minus 2 divided by 1, and then I have plus 2. What is it going to be? It is going to be 1 plus something, which is greater than 1. Anyways, it is positive. So what do I get? I get that when these stable equilibrium points are actually there, what is happening? What is happening? These two equilibrium points are actually unstable. They are not stable. Okay. So my this x is equal to plus minus of, it is unstable and not stable. While for r less than 1, my x is equals to 0 is stable. So if you can plot this, if you are able to understand that, that is fine, but I'll try to plot it. Okay. So if this is my r and this is my x, and if I consider that this is my r is equal to minus 1, what is happening? For r less than minus 1, my this is stable. And after this, it becomes unstable. Also, for my r less than 1, I have two other equilibrium points or fixed points which are unstable. Like this. So what kind of a bifurcation is this? This is subcritical pitchfork bifurcation. However, this is a very simple case and it was easy for us to solve. I'll also tell that how you can solve this using MATLAB, okay? Because it is important. Now, the previous question was based on a one-dimensional equation, but you can also have two-dimensional equations. So in case of two-dimensional equations, how am I going to solve this? So let us use this equation. So I have the equation given as this. So I'll write this as f1 of x, and this will be my f2 of x. Okay. So I can find the Jacobian as, I have to find the Jacobian. Okay, Jacobian is essentially used to linearize the system. Okay, so what do we do is that we linearize the system. Then we put in the value of the fixed point. Okay, and then we try to find out that how the system is actually behaving. Okay, so Jacobian, I'm going to find what is going to be the Jacobian. Del f1 by del x, del f1 by del y, del f2 by del x, del f2 by del y. So what am I going to have? I'll have mu plus y square minus 1 plus 2xy. Then I have 1, and here I'm going to have what? Mu plus 3y square. Now, as I told, first we are using Jacobian, okay, to write the system in this form. Then what we do is we put in the value of the fixed point. So what are the fixed point that I'm going to get? So let us consider the trivial case. Trivial case means x is equals to 0 and y is equals to. If you see, these are the two algebraic equation which you want to solve. Okay. So if you consider the trivial case is when x is equals to 0 and y is equals to 0. If my x is equals to 0 and if my y is equals to 0, both these equations are going to satisfy it. Okay, so if I consider the trivial case, what is going to happen? I'll put x is equals to 0 and y is equals to 0 there in this matrix. Then I have Jacobian as mu minus 1, 1, mu. So this is my Jacobian matrix. Now, if I want to know that what are the eigenvalues, so that I may know that or how the system's stability is changing. So what I'll do, I'll find the determinant of y. Okay, not y. Let us say that this is some a. Okay, j minus lambda I, which would give me mu minus lambda minus 1, 1 mu minus lambda. So it will be mu minus lambda. The determinant would be equal to mu minus lambda whole square and plus 1 is equals to 0. So I'll have mu minus lambda is equals to minus 1, from where I'm going to have mu minus lambda is equals to plus minus I, which implies my lambda is equals to mu plus minus I. So what is this? This is an imaginary value. So if you see that when my mu is changing, okay, so if my mu is here also the critical value is 0. You can see that. So if my mu is less than 0, I'm going to have what? Imaginary eigenvalue with a negative real part. So a negative imaginary lambda with a negative real part. What does it signify? It signifies that my system behavior is going to be spiraling in. Spiral in. It is going to go like this and reach the fixed point. Okay. When my mu is positive, what is going to happen? If my mu is positive, which is my imaginary lambda with a positive real part, then what is going to happen? My system behavior is going to be spiral out. Okay. And apart from that, what is another thing that is going to happen? Apart from having a spiral out, this makes the system unstable. Whatever the fixed point is, if I'm going to give even a very small, infinitesimally small perturbation, it is going to reach to infinity with no time. Okay, so this is the case. Apart from that, if you see that for mu is equals to 0, what is going to happen? For mu is equals to 0, my this lambda is going to be purely imaginary. Its real part is equal to 0, which means that it is going to hold a periodic solution. Isn't it? It is going to hold a periodic solution, which is not going to decrease or increase with time. If I give it some perturbation, it is going to follow that periodic path. Okay, so what does it mean? It means that this kind of a bifurcation is a Hopf bifurcation. And if you people remember that in the lecture, there were three conditions which were discussed. Not conditions actually, there were two conditions, but yeah, three conditions I would say. For Hopf bifurcation, we'll just see whether it satisfies or not. Your first one was that f at x naught and mu c should be equal to 0, which is satisfied, isn't it? At x naught and mu c, if the value of f is 0, because we, after equating it to 0 only, we got the value of x naught, isn't it? Second one is that your dxf has a pair of imaginary root, which is true in our case. This is essentially the Jacobian. And our Jacobian got a pair of imaginary root, or should I say eigenvalue? Root is not a correct word. Eigenvalue. It is having a imaginary eigenvalue. And the third was that for your mu is equals to mu c, your del lambda by del mu should not be equal to 0. Del lambda by del mu should not be equal to 0. Let me see. Lambda is mu plus minus I. Okay, so if I differentiate this lambda with respect to mu, what am I going to get? I'm going to get 1. It is not equal to 0. Okay, it is not equal to 0. It is having a value of 1. My del lambda by del mu is equal to 1, which is not equal to 0. So all these three conditions are satisfied, which means that this is a case of a Hopf bifurcation. Apart from that, there was also a thing that if these are satisfied, then for when it is crossing the limiting state or when it is crossing 0, 0, what is going to happen? It is going to create a periodic orbit. It is going to create a periodic orbit, which is also true in our case, because in our case, when mu, which is equal to mu critical, and in our case, mu critical is equal to 0. Okay, our lambda is going to be what? Plus minus I. And this plus minus I means that we are going to have a periodic orbit. A periodic orbit which is not going to spiral in or neither it is going to spiral out. It is going to have a periodic oscillation. Okay, so it is having a system is having a which type of bifurcation? The answer is that we are having a Hopf bifurcation. Okay, so now I'll be solving these last two questions. We'll be taking these two questions in MATLAB and we'll see that how we can use MATLAB to solve these kind of a questions, because if in any case if you are having equations that is having transcendental terms, sine, cos, something like that, then in that case you'll have to require to use MATLAB or some mathematical tool which would help you to solve it. Okay, so now I'll just connect my laptop. Okay, so is my screen visible? Okay, so if you see this question, this equation, this is actually your question number 7. This question, I'll share it in the PPT. This question number 7, where you have x dot is equals to x plus rx divided by 1 plus x squared. So if you remember, as I have discussed it, that with the change of parameters and by the limiting value, so here my limiting value of r was, it was -1. Okay. So my limiting value was -1. Okay. So for now, I don't know that what kind of a bifurcation is going to be in the system, how the system is going to be. For now, I don't know. I just know that there is a limiting value which is -1, and I know that there are three kind of fixed point. One is your x is equals to 0, and the other two are dependent on r. Okay. So I know that the limiting value is -1. So what I'll do, I'll just consider for now that my r is greater than -1. Let us suppose that my r is 1. So let us see what is going to happen. So this mu is actually r. So I'll just take it as 1. And my initial condition, I'll take it as, first I'll take it as 0, 0. Let us see what happens at 0, 0. Okay, 0. Because this is a first order differential equation, so I need to put only one initial condition. Let us see, which is 0. See, what is happening? With time, the position is not changing. If the system is at 0, it is going to remain at 0. Okay, now I'll just give it some perturbation. Let us suppose 0.1, the positive direction. Now we'll see. See, how much perturbation did I give? It was just 0.1. And if you see that within 50 units of time, the system has gone to 2 into 10 to the power 21. What is this? This shows the instability in the system. This shows that my this 0 is actually a unstable fixed point. If my system is at that point, it is going to remain at that point. But if even a very small amount of perturbation is given to the system, it is going to go to infinity. Now, for example, if I want to give it some perturbation in a negative direction, minus 0.1, I'll just make it small, 0.001. Let us see what happens. See, even if I gave a perturbation very small in the negative direction, the system has gone to minus 2 into 10 to the power 20 within 50 units of time. This shows that my system has is unstable, and this my 0, which is my fixed point, is actually a unstable fixed point. If it would have been a stable fixed point, the system would again come to 0, with time. Okay, now if I take now my limiting value was minus 1. So let us assume a value minus 2 and let us see how the system is behaving. First, I'll again take 0, 0. Now I know that for r is equals to minus 2 in this equation, for r is equal to minus 2, I'm going to have two fixed points. Sorry, three fixed points. One is your 0, x is equals to 0, and the other two are the plus minus of under root 1 minus, okay, no, plus minus under root of minus 1. Maybe I'll just write it here. It would be better, no? Your x will be equal to 0, and then you're going to have plus minus. You'll have minus of what? You have minus of 1 plus r, and then you're going to have one more, which is your, let us copy it from here. So these are your three fixed points. Okay, so if your r is less than minus 1, so what is going to happen? All these three equilibrium points are going to exist. So now we'll put minus 2 and 0, 0, and let us see what is happening. Okay, so if my initial state is 0, 0, it is at 0, 0. Now let us give it some small perturbation. Let us suppose 0.1. What happened? In the initial, like before this, when I took mu as positive 1, what was happening? If I was giving some small perturbation, this system was getting unstable. Okay, it was not reaching your 0, 0. It was going to infinity. Whether the perturbation was given in the positive or negative direction, it was going to infinity. But in this case, what happened? Now I have three fixed points, and I can see that now if I'm giving a small perturbation from 0, 0, it is coming back to 0. Now my 0, 0 has become a stable fixed point. Initially, it was unstable. For r greater than minus 1, it was unstable, and now it has become stable. And if I want to give some perturbation in the negative direction, it is again coming to 0, 0. But there is one thing that you people need to notice is that this stability is only up to a certain value. Okay, it is only up to a certain value. If I put this minus 0.1 as maybe 2, this is again going to go to infinity. Why? Because if you remember that this is a case of a subcritical pitchfork bifurcation. So as soon as the system is going to come in the vicinity of your unstable fixed point, okay, as soon as it comes in the vicinity of your unstable fixed point, it is going to take the system to infinity. at that place, the dominance of your stable fixed point, which is 0 comma 0, is not that much. Okay, the power of then the unstable fixed point is much more higher than that of the stable fixed point. Okay, similarly, you can see for the positive value also. If I take positive 2, it is going to infinity. Let us see for 1 what is happening. Okay, now, so this is your case. If you consider for 1. See here, for 1, if I am giving the system an initial state of 1, it is actually remaining at 1. Can you tell me why? This is because I have taken r as -2. If my r is -2, what is it going to be? My fixed points are now plus minus 1. And this plus minus 1 is essentially now a unstable fixed point. That is why my system, if it starts from plus 1 or minus 1, it is going to remain at that point because it's an unstable fixed point. However, if I give it some perturbation, let us suppose 0, 0, 0, 1. Let's see what is going to happen. Infinity. Your 1 was an unstable fixed point, and this unstable fixed point has the property that even if you give a very, very small perturbation, it is never going to return at that point. Okay, so this is the reason that this is happening. If I take -1 with some small perturbation, see, the system is again going to go to infinity. And if I reduce this small perturbation from the system and I consider it as -1, the system is going to remain at that point till t is equals to infinity. Okay, so this is how you can use MATLAB in order to predict that how or what is the system's behavior, what kind of a bifurcation is actually occurring in the system. Because see, for this equation that we considered over here, it was an easy equation. It was an easy equation for us to solve analytically, isn't it? It was easy for us. But if you consider a much more complex system by introducing sine, cosine, tangent, or maybe ln, something like these in the system, what is going to happen? See, if I even if I consider x dot is equals to x plus sine x, so I'll have the equilibrium equation as x plus sine x is equals to 0. So I'll have to find the value of x for which this is satisfied. And it may happen that there can be many equations. Anyways, the number of solution that I want to get, I cannot get it by analytically solving it. Okay, I require some mathematical tool. Or either I can use some trial and error method, but it would take a lot of time. So it is better and it is preferable that you use MATLAB. You have the equation of motion, you try to simulate. You first find the critical value of the parameter. Once you have the critical value of parameter, you know that for what value you have to see. You have to see in the vicinity of that parameter that's what is changing. For example, if I have r is equal to -1, I'll have to see that what is the variation of the system performance for r less than -1, for r greater than -1. And from that variation, I can predict that whether the system is having some kind of bifurcation or not. Like for example, for this kind of a system, when I used this MATLAB, I knew that for r greater than -1, what was happening? The system was having only one fixed point, that was 0, and it was unstable because if I was perturbing it, if from a very small amount from 0, it was going to go to infinity in both the positive and negative direction. However, when I took r less than -1, what happened was that now I was having three fixed points, in which 0 was my stable fixed point because whenever I was giving some perturbation from 0, it was again coming back to 0 wait time. However, if I was giving a perturbation very large with respect to 0, or should I say greater than 1, then what was happening? The system was actually going to infinity. Even from 1.0001, a very, very small perturbation in the positive direction from 1 was taking the system to infinity. And if I take the perturbation as, like, if I consider like 0.9998, This is also a very interesting thing, and if I simulate, see what was happening. A very small perturbation from 1 but in the negative direction or towards 0 is actually taking the system to be stable. So if you see that in practical case, if I have a variation of 10 to the power minus 12 in the initial condition, it is going to either make my system stable, or it is either going to take my system to infinity and cause a catastrophic failure. Isn't it? That is why dealing with non-linear system is a very difficult task. Okay, because you have to take care of even a small variation, and generally we avoid the range or which is near to that of the unstable equilibrium point. Okay, because that may lead to catastrophic failure, which you can see here. That is very small variation in the equilibrium state is actually taking the system to infinity, and a very small variation is also taking it to stable state. Now coming on to this equation. This was a first like a one-dimensional equation. Now coming on to this question number 8, which was a two-dimensional case. So in this case, how am I going to deal with the system? So you can see that here there are two dimensions, x dot and y dot, and we need to know that in both the directions of both the eigenvalues are positive, negative, or what kind of a bifurcation is actually occurring in the system. Okay. So we'll take this case here. This is our case. This I'm going to change as capital X, and this is going to be not velocity but capital Y. Okay, so if you remember that for this case, I was having how many fixed point? I was having whatever, I am just taking my trivial solution, which is 0, comma 0. And my eigenvalue was coming out to be, I'll just add the eigenvalue over here. So my eigenvalue was actually coming out to be lambda is equal to your mu plus I, and one was mu minus. So these two were my, oh sorry, mu minus I. So these two were my eigenvalues. So now if you see here, my critical value was what? It was mu is equal to 0 only. So if I see about my critical value, so now what do I have to do? As I have discussed earlier also, I have to see the critical value. Critical value is mu is equal to 0. So I'll see the system dynamics for mu, let us suppose zero point 0.1 or zero point 0.5, and I'll see the variation of system dynamics for mu less than 0, which would be minus 0.5, and then I'll be able to predict that how the system is going to behave. Okay, so for now I'll just consider that my mu is, okay, for example, it is minus 0.1. Okay, so from my trivial case, first I'll consider 0, comma 0. Anyways, see, 0 with time it is not changing. Now I'll give it some small perturbation. See, now you see what is happening to the system. See, so you can see that for my mu, for my mu less than 0, what is happening? For my mu less than 0, the system, I have given some small perturbation to the system, and with time it is showing a spiraling in behavior. Okay, so what is happening? The amplitude of oscillation is reducing, and finally the system is reaching my position 0, which we also predicted from the eigenvalue, because my eigenvalue was like this, and if my mu is negative, it is going to show a spiraling in behavior. So this was one thing, and now I want to see that what is going to be the system behavior for mu greater than 0. So let us just take it 0.1. Okay, you can see that what MATLAB is showing. It is showing that failure of the system is happening. What kind of a failure is happening in the system? You can see over here. So MATLAB has this ODE command as a built-in. property that when the system goes to infinity in a very small time, it is going to stop the simulation, and it's going to inform us that okay, the system is getting unstable, that the system is going to infinity. You can see what is happening. With time, the system has going to a very large value, and here you can see a spiral out behavior. If I zoom it, see what is happening is the system is going out, it is going to infinity. So what did I see? I saw that with the increase of mu, however, now also if I consider again 0, comma 0, my system is still remaining at this point. So what did I see? So if you remember that in case of a hop bifurcation, there was a thing that was discussed in class, that there was a fixed point and then there was a stable cycle and then there was an unstable cycle. So what is happening? We are having a fixed point and then there is a unstable stable cycle, spiraling in cycle for mu less than 0, and then there is a spiraling out cycle which is an unstable cycle for mu greater than 0, and hence this is a bifurcation. Okay, so this is how you can use MATLAB in order to know that how the system is actually behaving. Okay, till now whatever the questions we have discussed in which I've asked that what kind of a bifurcation is occurring, it was easy for us to solve, because but now if I introduce, like you have in your assignment, you have some questions which include sin x, cos x, such kind of a terms. So in that case, it is preferable that you use this logic which I have discussed here, that you use this logic and then you try to solve those equations. That would be very helpful for you. The first thing that you have to do is you have to find the critical value. You find the critical value of the parameter, and then you have to see that how the system is behaving at that value, for a value greater than the critical value and for a value less than the critical value. So this variation of the system with that of the parameter is going to show that how or what kind of a bifurcation is actually occurring in the system. And it is very essential that we know that what kind of a bifurcation is occurring in the system, because if you see here that when I give it a very small perturbation, the system was actually going to infinity with a very small time, which would lead to catastrophic failure. So it is very important that we know that how the system is behaving. See, the amplitude of oscillation is increasing and it would go to infinity with some time. Okay, so it is very important that we know which kind of a bifurcation is there in the system. So if there is not a occurrence of a unstable thing, then it is can be used for practical application. However, if it is having some kind of a instability, then it is essential that we avoid either the parameter values for which the instability may occur, or either we change the dynamics of the system, we change some parameters of the system such that it can be avoided, that such kind of a vibration can be, sorry, bifurcation can be avoided. Okay, so I hope that the questions are clear. Is there any doubt for any of the question? Anyone having any doubt? Okay, so this is it for today's live session. I hope that you people were able to understand what I'm trying to say, and I hope that you'll be able to solve the questions. So that is it. And if you have any doubt, you can ask in the next live session. Okay. So thank you so much.
Thank you, madam.
Thank you.